All right, guys, I'm going to do a 4-part review for you guys so that we can cover all the topics that are in Chapter 16. So let's go ahead and get started. 16.1 is about the properties of solutions. So here are the basic items that you need to cover. Substances dissolve at different rates depending on a couple factors. So if you stir a solution, it's going to dissolve faster. If you increase the temperature, like we saw in the lab that we did in class right before we had to, go to our homes, you increase the temperature, it's going to increase the dissolving rate, so it's faster at dissolving. And then the surface area, if you, for example, cut a piece of ice, it will dissolve a lot faster than if it's just one solid block. And then pressure also has an effect on this. And solubility, as you saw in the solubility graph, is the units are grams per solute, grams of solute in 100 grams of solvent. And this is what you used right here. This is what you used to solve for the unknown substances in your lab that you should have turned in. So that's pretty much 16.1. It's figuring out how to make something dissolve faster or slower depending on these 4 variables, and then determining just the basic solubility of a substance. And then as we move on, we're going to move into different calculations. And I do want to make one note that for all of these values here, so for example, stirring, so you increase stirring, increase temperature, break down, make the surface area larger that's exposed to the solvent. All of those are for most solid substances, but for gases, it's the complete opposite. So I'm going to type that in over here. For gases, it is opposite. And just to give you a little example, I talked about this in class, but if you missed it, for example, if you take a soda and you increase the temperature, more of the carbon dioxide will leave, not more of the carbon dioxide will dissolve. In order to dissolve more carbon dioxide, you have to make the soda colder. So again, gases are the opposite of this when it comes to dissolving. So that is 16.1. All right, here goes. This is 16.2. It covers the idea of molarity. So we looked at molarity when I had you guys answer that question about cereal and milk versus milk and cereal. So I'm going to cover molarity here, and then in a later section, I'm going to cover molality. So I'm going to use an example I normally do from class, along with this second equation here, which is M1V1 equals M2V2. So this is how to dilute or figure out how much of a concentrated solution I need to make a less concentrated solution. So one thing to note is that when you dilute something, and I wrote it down here, when you dilute it, you actually increase the denominator, so you're increasing the amount of solution, but you're not actually changing the number of solute particles. So that's exactly what this example will be. So before you guys show up to class, I normally take a solution of really concentrated hydrochloric acid, so 12 molar, and I make it less concentrated to make it a little bit quote-unquote safer. Still somewhat unsafe, but it's not as unsafe as it would be in full concentration. So what I end up doing is I take my concentrated solution, so my M1, and then my V1 is my unknown because I need to figure out how much of the concentrated solution I actually need to pour into the amount of water that I want. So then I set this equal to my M2 and my V2. So let's say that I want to make a 1 molar solution like this. So I would write 1 molar right here. And then I would multiply that by my volume that I want. So in this case, I want 100 milliliters, but I want to make sure that's converted to liters because if you look at the molarity formula, it is liters of solution. So in order to convert that, I just divide by 1,000. So it's going to be 0.1 liters. So what I end up finding is that I do my calculations of 1 times 0.1, so that ends up being 0.1. And then in order to solve for V1, I'm going to divide both sides by 12. So on my calculator, I divide by 12, and then I get a value of V1 to be equal to, let me get a number for you. It is going to be 0.0083 liters, Or if I were to convert it back, which is multiplied by 1,000, it would be 8.3 milliliters. So then, now that I have my values, here's what I would do. I would take my concentrated solution and I'd pour 8.3 milliliters in a container first. And so this is the putting the cereal in first. And then I would raise the volume to the amount that I actually want. And in this case, I want 100 milliliters. So I would probably do this in a graduated cylinder. I would pour this 8.3 milliliters of concentrated solution, right? That's this one right here. I'm highlighting it for you so you can see it. So 8.3 milliliters into the solution. And then I would add water to it. And I would raise the water level up because it already has 8.3 of the concentrate. I'd raise it up to my 100 milliliters that I want. And I would have exactly 100 milliliters of diluted or 1 molar solution. So that's how to do those calculations. In this section, you also had a volume by volume percent. So this is a little bit simpler of a calculation. You take the volume of solute divided by the volume of solution, and you multiply it by 100. I saw a lot of you guys did very well on this one, so I'm not going to go too much over it, but if you have questions, you can email me about that or come to my office hours on Wednesdays and Fridays. All right, 16.1 and 16.2 kind of go together. So it talked about how to increase or decrease the rates of dissolving, and then it talked about different concentrations and calculations. 16.3 and 16.4 are relating to each other. So in 16.3, it covers the ideas that will eventually be used in 16.4 to do the calculations. So let me go over 16.3. There are 3 main colligative properties that you want to know about. Number 1 is the vapor pressure lowering. So vapor pressure is the amount of molecules that are above a solution when something is vaporizing or evaporating. So the molecules vaporizing are vaporizing, the ones that want to vaporize are competing for space near the surface of the liquid. So when you add salt to water, the vapor pressure is being lowered for the water because the molecules of water and the molecules of salt are competing for who can escape from the liquid first. It would be like a very crowded room where you add more people, which means it makes it more difficult to leave the room if there is some sort of reason to escape the room. So if there's a fire or something. So that would be an example of that. Freezing point depression. So as I said here, specifically for water and water crystals, they get disrupted from forming crystals. So if you've ever seen a snowflake, snowflakes actually form because water creates a crystal. And so when you add a substance to it, a solute, like ice, so an example here, adding ice to salt, or salt to ice, my bad, it makes the freezing point even lower. So on a road, if there's a lot of ice, they throw salt on the road because what happens is the ice, quote unquote, melts, but it's not actually melting. The temperature is still 0 degrees Celsius. It is that it needs a lower temperature in order to refreeze. So unless you put that ice back in a freezer or you keep removing heat, it will still be a liquid, but it will be at 0 degrees Celsius. So this is actually what you use to make ice cream at home. Is you want to make the ice, salt, water really, really cold around the ice cream. And then the last one is boiling point elevation. It's very similar to vapor pressure lowering. Molecules are competing to escape from the liquid. So when you put water and salt on a stove and you heat it, it requires more than 100 degrees Celsius to boil the water. So normal boiling point of water is 100 degrees, which means that water coming out of your tap or clean water boils at a higher temperature. So pastas, some of them require a higher boiling point. So they in the directions require you to add salt. So just to review really quick, vapor pressure lowering, That means that the molecules are competing to escape from the liquid. Freezing point depression means that if you add a solute to a solvent, it makes it harder for it to crystallize or form a solid structure, so it makes it more difficult to freeze, which means you have to lower the temperature more. And then the last part of the review is that the boiling point increases when you add a salt or something to it. In the next section, 16.4, we're going to use these three colligative properties, and specifically two of them, but we're going to use them to help solve some equations and get some actual values. All right, in 16.4, we covered the topic of molality and then did some calculations on actually calculating how to find the amount of solution that we need, and then the amount of moles of a solute that we need to put in a solution to lower the freezing point, which would be right here, delta TF, and then to increase the boiling point, delta TB. So this is probably the part that you guys had the most trouble with as you were going over 16.3 on the computer. So let me just explain all of these. So delta TF and delta TB, that's the change in the temperature. So either lowering the freezing point or raising the boiling point. So an example that I can use is, let's say that you're adding salt to a solution. So you would want, let's say you want the freezing point to be 10 degrees lower than it actually is. So I'd put a negative 10 degrees. Celsius. And so then I would set that equal to what is the Kf, or the molal constant for freezing point depression. So this is a value that you can look up. So Kf, you can look it up. It's not a problem. So what I would do is I would Google this. So if I were to look it up on Google, I would type in NaCl Kf constant. And it would return a value of 1.86 degrees Celsius per molal. So 1.86 degrees Celsius per molal. And so I would italicize this right here because it's molality. Okay, and then I would multiply that by the actual molality that I want. So let's assume that we don't know what that is. So I would just put a question mark for the molality. So moles of solute per kilogram of solvent. I'm going to abbreviate this just to make it easier. Okay, and then the last thing is I would multiply that. Let me make this a little bit smaller so it all fits on the same line. So then I would multiply by I. And I is pretty important to understand. I relates to dissociation. So I'm going to put this down here. Relates to dissociation. Actually, types. Dissociation. So for NaCl, we know a couple things. It is ionic, which means that it will separate out into ions. So in this case, it will separate it into Na ion. So that would be Na plus, and it separates it into Cl minus. So what that means is that in this case, I would be equal to 2, since it created 2 ions. So one rule of thumb for this is that if it is ionic, it will have an I that is greater than 1. But if it's any other compound, if it's molecular, which means it has covalent bonds, I will always be 1. So since we're doing this for NaCl, I would need to multiply this by a 2. So that would be my I right here. So I right here, if I highlight it, is related to this value right here. Okay. All right, so I should have highlighted here since we're doing the freezing point depression. So you get the idea. So now the only other piece of information I would need would be the amount of kilograms of my solvent, so the amount of kilograms of water, or I would be needing to know the amount of moles. But in most calculations, you are given the amount of water that you have, but you're asked to figure out the number of moles, or in the questions that you saw, the actual molarity. So then you would need to be given one of those two. So in the case of, let's say, the question in the book, or a question from the book, you could be told that you have 5.5 kilograms of solvent. So then you would have to solve for this value right here. So let me just review really quick, just in case you got a little bit lost. So delta T, whether it's for freezing point depression or boiling point elevation, is just the change in temperature. So freezing usually will be a negative value because you're going down, and boiling point will be a positive number going up. But either way, it's the change in temperature. So that's what delta means. Kf, that's a value you would look up for each specific compound. So that is either given to you, so you don't have to memorize these ones. So these ones are given to you. The Kf, which is the molal freezing point depression constant, or the molal boiling point elevation constant. And then molality is M here. This is a value that you do need to know, and it's based off of the formula up here, which is molals of solute, which I have here, and kilograms of solvent down here. And then the last one is I. I know this is not in the book, but it's very important to understand. So that's dissociation amount. So it's the amount of ions that it makes. So sodium chloride makes 2. If you have something like calcium chloride, you would have a 3 because calcium is a +2, and then you would need 2 chlorides. So it'd be a total of 3 ions. So realistically, the only time that I is anything more than 1 is going to be for an ionic compound. So you have to remember a little bit of previous chemistry to figure out what that number is. So then once you do all of this, you would solve for the number of moles here. And sometimes you're asked to figure out the actual molarity. Well, not molarity, but sometimes you can use this to figure out molarity because you can have the moles of solute. But in the questions in the book, you would probably just use this to find the number of moles that you need, or the number of grams that you have, because you can take the molar mass of sodium chloride and figure that out. So if I were to continue and actually solve for the number of moles of NaCl, I would figure out that it was 14.8 moles of NaCl. And so that's my answer. Now, this doesn't really help us much in the laboratory. We would want the mass of NaCl. So in order to figure that out, I would have to take my number of moles. And as I've said many, many times, if you start with moles, you would multiply, right? So you're going to multiply by the molar mass of sodium chloride, which is actually 58 grams per mole. When you do this, you get 857 grams of NaCl. So here's how this would work. If I have 5.5 kilograms of water, so instead of solvent, I'm going to change this to water. Say I have a big bucket of water and I want to boil it, right? So I have 5.5 grams of it. I would need to measure out 857 grams of sodium chloride. And not boil it, but I wanted to freeze it. I would have to put 857 grams of sodium chloride in that water, and then it would allow me to get the water down to a temperature of -10 degrees. So that means when it froze and became ice, the temperature of that ice would be -10 degrees Celsius, not 0 degrees Celsius like normal water. So that's how this works. That's how you solve these. If you still have questions, again, I have office hours on Wednesdays and Fridays between 10 and 11 a.m. And I'm free for emails if you need to answer any questions or you have any questions. So I hope that helps, and let me know if you need additional help.